Hello everyone, I'm Zeng Ziyun, and here I will present our work, Motion-Aware Graph Reasoning Hashing for Self-Supervised Video Retrieval. Video retrieval aims to find values relevant to a given query from a large-scale database. Video hashing aims to project high-dimensional real-value data into compact binary codes in a similarity-preserving way. Then, the binary codes can be stored efficiently and support fast bitwise Hamming distance computation. However, existing video hashing works yield poor performance. The reason is twofold. Firstly, lack of label supervision. Since annotating videos is more labor-intensive, it is hard to construct large-scale label datasets, for example, ImageNet. Secondly, modeling the temporal dependency within frames is challenging. Therefore, efficient and effective unsupervised video hashing, UVH, has become a valuable research topic. Most state-of-the-art UVH methods take temporal dependency into consideration. They mainly adopt RNN, LSTM, and transformer to handle sparsely sampled frames. Some latest works have shed light on graph reasoning, GR, in the field of video content understanding, but they merely learn the semantic relation between objects within a single frame. However, without explicit motion guidance, a module may be trapped on objects or scenes, as these semantic components are easier to learn in sparsely sampled frames. Nevertheless, directly extracting clip-wise motion features via specific modules is not practical in inference due to largely increased computation overhead. As shown in Table 1, the G-flops of the clip-wise module is 10 times more than that of the other two frame-wise modules. Hence, it is a challenge to exploit motion information as well as keep inference efficiency. Our contribution is threefold. Firstly, we propose a novel self-supervised video hashing method, motion-aware graph reasoning hashing, in which we explicitly module the motion information and take an early step to adopt graph reasoning to module the temporal dependency. And we design a dual-branch architecture to produce general and motion hash codes separately, as well as a combination of intra and inter-branch contrastive objectives to simultaneously improve branch-specific hash codes and force the general hash codes to preserve more motion information within frame-wise inputs. Extensive experiments on two public benchmarks, FCVID and ActivityNet, show the superiority of the proposed MAGRH. Benefiting from the motion guidance, our MAGRH surpasses state-of-the-art methods by a large margin, with fewer inference frames. This is the framework of the proposed MAGRH. It consists of two branches, the main branch to extract frame-wise general features, and the auxiliary branch to extract clip-wise motion features. We first sample two non-overlapping sets consisting of T frames or clips to construct two views for each branch. Then, we extract general features and motion features from frame and clip sets respectively via a general feature extractor and a motion feature extractor. Then, we perform sequence-level graph reasoning to explore the temporal information. Here, we omit the superscripts for general and motion features for simplicity. Specifically, for each graph reasoning module, the GRM, we first project the input sequence into the dimension div subscript h via two linear layers denoted as phi. Then we add a learnable position embedding this subscript p to each sequence. Next, we add a learnable branch-specific embedding z subscript m and concatenate an extra AGG token at the beginning of the sequence, where the AGG token is computed by applying max pooling on the input sequence. Then we compute the adjacent matrix by a simple matrix multiplication with row-wise normalization, where G subscript 1 and G subscript 2 denote two projections. Then we perform air layer graph convolution. It is worth noting that we conduct graph reasoning with two consecutive GRMs. I, branch-specific GRM, and branch-agnostic GRM, where the weights are individual for the former and the weights are shared for the latter. This design makes training more efficient as we prevent information loss for the general and motion features. As for the hash layers, after obtaining the output of branch-agnostic GRM, we apply an average pooling along the temporal channel. Then we project the results into dimension d subscript b and binary it by a sign function, where d subscript b denotes the code length. Inspired by the recent success of contrastive learning, we first propose a hashcode-based contrastive objective, namely air subscript intra-CL, to learn the intra-branch hashing function for the two branches simultaneously. Beyond it, we derive an inter-branch contrastive objective, namely air subscript inter-CL, to transfer motion knowledge from the auxiliary branch to the main branch explicitly. Finally, we add an L2 regularization term to reduce the quantization error between the real-valued vectors h and the hashcodes b. The overall learning objective is the sum of the above three objectives, and the full derivation can be found in the supplementary material. In inference, the auxiliary branch is removed. The hashcodes are solely produced by the main branch, so it is computationally efficient because only frame-wise inputs are required. The similarity between a given query and the database items can be calculated via bitwise Hamming distance quickly. Here is the main results. We conduct experiments on two widely used public benchmarks, FCVID and ActivityNet. As shown in Figure 2 and 3, our MAGRH achieves state-of-the-art performance in terms of MAP at top K. According to Figure 4, our MAGRH achieves comparable performance with clip-wise motion features, while the computation cost is affordable as the input only requires T frames in inference. We further conduct ablation studies on robustness, efficiency, architecture, and contrastive configuration. More detailed explanation can be found in our paper, and more results can be found in the supplementary material. Thank you.